Hey everyone, welcome to our first lecture, starting off chapter 1, which will begin our really flying super fast review of what you learned a little while ago in Gen Chem. So just to get us started, trying to think about chemistry and how it really makes up everything. Everything is made up of chemicals, and those chemicals are made up of individual atoms. So we can't forget that. Anything in your life, everywhere around you, the food you eat, the people that you talk to, the desk you're sitting at right now, the computer you're looking at is made up of atoms. And you'll probably see a bunch of different cartoony representations of atoms around where we have some kind of a central nucleus looking thing. And around that, we'll have a cloud of electron density that usually will kind of just look like a circle or a sphere, but it is going to be more complicated than that. We'll get to that a little bit more later on. So in OChem, we really are focusing on groups of atoms all together in individual molecules. And then we like to look at the properties of those molecules and see how they compare to other different types of molecules, or how we can adjust the molecule to adjust the properties. In organic chemistry, we have a few favorite atoms that we like to favor over the other ones, and those are carbon and hydrogen. So when we say organic chemistry, we don't mean that we didn't use pesticides on the food that we grew. It's not that kind of organic. We mean that it's based mostly in carbon and hydrogen. There are some other atoms that we do really love that you're going to see a lot. So those common sort of other featured favorite atoms are oxygen, nitrogen, sulfur, phosphorus, and usually we get a lot of use out of the halogens as well. So that's fluorine, chlorine, bromine, and iodine. Keep an eye out for those. They'll definitely be big players this semester. So we've got our atoms, right? And we don't care quite as much about the nuclei, really. What we're more focused on actually is the electrons. Because electrons are what actually make and break chemical bonds, and they're the things that cause reactions to occur. So we have two major types of bonding that we're going to focus on, one more than others. I guess sort of one more than the other, I should say. And that is ionic versus covalent bonding. So our ionic bonds just means that we made ions, and so that we're giving one atom more electrons and the other one is taking them away. So that means that we'll have things with positive charges, those are cations, and negative charges, or anions. So in order to make a cation, something gives up its electrons. To make an anion, something accepts an electrons. So this isn't going to be the main focus of organic chemistry, but we will see it. So kind of keep it tucked in the back of your mind. We're not going to see a ton of it, but it will be in there. What will be our main focus, on the other hand, is the covalent bonding. So a covalent bond means that there's a sharing of electrons. It's not giving and taking. It's either going to be an equal or unequal sharing of electrons. So if it's an equal sharing, that's what we call nonpolar, a nonpolar covalent bond. If it's an unequal sharing, that is a polar covalent bond. And we'll talk more about what makes a polar and nonpolar bonds later on. We're going to look at electronegativity for that. And I like to abbreviate electronegativity as big capital E, capital N, because it's a long word and it takes a while to write out. So more on that later. First things first, we need to think more about covalent bonding and put it into practice with some Lewis structures. So hopefully we have a little bit of a memory in the back of our minds about what Lewis structures are and how to draw them. We'll do some practice right now so that you can get back up to speed. Let's start with water as an example. So if we were to draw the Lewis dot structure of water, that's when we just take the separate atoms. Here's O and two H's, and then put in dots that represent their valence electrons. So hydrogen each have one valence electron. Oxygen has 6 valence electrons, and you can see these trends on the periodic table. If they're feeling a little bit fuzzy, that's okay. We have some time to review them. So with those dots in place, now we can pair up pairs of 2 electrons together, and those are going to form our covalent bonds. So we can see that kind of these two are nearby to one another, those two are nearby to one another, and then these two here are already sort of paired up with themselves. So that's one way to draw the Lewis dot structure for water. Now, once you get to be drawing lots bigger, more complicated molecules, doing each individual dot is going to be pretty cumbersome. So we start to skip over that and take some shortcuts. So if we were to simplify the Lewis structure of water, we would again draw in the oxygen and the hydrogens, but instead of dots, we're just going to draw in a solid line for any bond that's formed between 2 atoms. So over here, when the oxygen and hydrogen are sharing that pair of electrons, that forms the covalent bond, which we can just simplify by drawing like that, and the same on the other side. Those other 2 pairs above and below the oxygen though, those ones aren't participating with any other atoms. They're by themselves. They're what we call lone pair electrons. So we just draw them in like so to remember that they're there, because those will do a lot of the chemistry we're going to see this semester. So that's the difference between our Lewis dot structure and our full-on Lewis structure. So there are a few things that are important to remember as you're drawing Lewis structures. One of those is the octet rule. So the octet rule told us that in order for anything to have, any atom to have a full octet, it must have 8 electrons around it. We can go and check that for oxygen here in our previous example, that in the Lewis dot structure, we had 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. And we're counting those lone pair electrons and all of the electrons that are shared in any covalent bond. So we want to always obey the octet rule, except for a couple of specific times. If we have our hydrogen atoms, you could see those definitely don't have 8 electrons around them. And that's because they don't have the orbitals to hold 8 electrons. They only need 2. So they should have just 1 bond or 2 electrons around them at any time. Now, the other exception that you might see, probably not a lot in this course, but boron is one of those weird ones. Boron can have either 6 or 8. It's okay to actually have 6 for some reason. Boron's kind of a weird one, and that's all right. The other exceptions that definitely will be more common are sulfur and phosphorus. They can have more than 8 because they have access to d orbitals, which gives them more room to fill in extra electrons. So don't worry too much about that just yet. We'll see some examples later on. The other thing to remember with Lewis structures is how to analyze formal charges. So there is a formula to calculate formal charge in your textbook if you like that kind of thing. For me, it's simple addition, subtraction, division. That's still too much math for me. I'd rather not do that. What I like to do is start to look for patterns. So definitely fall back on that formula if you need it for a while, but you'll start to see as we look at more and more structures, common patterns emerge. So that's why I like to fill out this table here to help you see the differences and similarities between some of the most common atoms we're going to see, carbon, nitrogen, and oxygen. So let's start with what it takes for these atoms to be neutrally charged. Hopefully we can remember from Gen Chem that carbon likes to have 4 bonds around it and no lone pair electrons. So we haven't seen any carbon-based examples yet, but we'll get to practice with a lot of them. It doesn't like to have any lone pair electrons and 4 bonds. No more than 4, never ever. So similarly, nitrogen likes to have a few bonds, but it also likes to have a lone pair of electrons. So it'll take 3 bonds and 1 lone pair of electrons. And then if we kind of keep going, you'll see this pattern continues. Oxygen, as we can see in the example above for water, likes to have 2 bonds and 2 lone pairs of electrons. Not too bad, right? So it kind of follows in this nice pattern. Now, if we think about what would it take for these molecules, these atoms to have a negative charge, that means that we're sharing less electrons and holding on to more of these electrons. So what you'll see happen is that carbon can't have any more than 4 bonds. So we reduce 1 to 3 bonds and give it a lone pair of electrons. If it has those 2 electrons sitting on itself, that's more negative charge. So we get a negative formal charge. Same with nitrogen, reduce the number of bonds, increase the number of lone pairs. Same for oxygen. You'll start to see these patterns emerge more as we look at more and more structures, so just tuck this chart in the back of your mind for now. On the other side, the literal flip side of positive charges, now we just need to use lone pair electrons and share them, because if we kind of give up a negative charge, we're taking on more of a positive charge. So I'm going to actually start at the bottom and say for oxygen, we increase the number of bonds and decrease the number of lone pairs. Same with nitrogen. We give it instead 4 bonds and 0 lone pairs. But I already said carbon can never have more than 4 bonds. So this one box kind of breaks the pattern a little bit. But we reduce the number of bonds to carbon. So that's 3 bonds. And then we also remove the electrons. So if it has 3 bonds and no lone pairs, then it's positively charged. There are a couple of other formal charges that you may see around. Halogens are a big one. But go ahead and take a look at those later on. These are the patterns that are going to be most useful to you right away. So let's take a moment to do some practice on drawing Lewis structures just to see how you're doing. And there will be a couple of quiz questions in the video for you to answer just to check your progress. These are not worth any points toward your grade. So first off, HCN. Let's draw the Lewis structure for that. Go ahead, pause here, make your guess, answer the video question, and then we'll look at the answer together. So to draw any Lewis structure, I have a set of rules that you can refer to, but I like to just draw out all of the atoms. And then sometimes I'll do that dot method of saying, oh, I know carbon has 4 and nitrogen has 5 and hydrogen has 1, and I'll just draw those in. Like so, and then kind of connect the dots, literally. So 1 from that carbon to hydrogen, but we can't make any more bonds there. We need to make more bonds to nitrogen. So there's 1. And now carbon doesn't have its octet, so we have to keep making bonds until everything has its octet. 2, 3. So that looks a little wonky. We'll clean it up in a second. But now if we check, hydrogen has its 2 electrons. Carbon has 2 here, 4, 6, 8. So carbon looks good. Carbon has 8 electrons. Remember, each one of these lines represents 2 electrons. And then nitrogen has 2, 4, 6, and 8 there with that pair. So the Lewis structure for HCN looks cleaned up a little bit nicer. Like that. Did that match what you guessed? Let's try the next one. Pause here, make your guess. For CO3 2 minus, in the case where we have a bunch of repeat atoms, I like to put whatever's first in the middle and then kind of spread the rest around the outside. Just looks nicer that way. And again, you can do this any way that you like. I'm going to just kind of follow this method that I have been, filling in the dots and connecting them. Okay, so if we just make a single bond to everything, that doesn't really look so nice. So, and then there's that 1 left on carbon. So we'll go ahead and make a second bond from carbon to one of these oxygens. But then we're kind of left with a few of these little awkward one-off electrons here and here. And that would be a problem. I didn't account for the -2 charge in our ion. So in order to counteract that -2 charge, you have to add in extra electrons. Again, you can review the rules that I've put online to just double check that. So if we've put those -2 in to account for the charge, now all of those oxygens, go ahead and check them. If you feel unsure, have their octet. The carbon has its octet. And so that is the Lewis structure for this CO3 2- anion. And again, it looks pretty much like that. I'll clean it up a little bit to make it nicer. Essentially the same thing. I just rotated it to put that double bonded oxygen on the top. How are we doing? Hopefully doing okay. Let's try this next one. This is the biggest one so far. Pause here, make your guess. Again, I'm just positioning all those oxygens around, and then I don't really know where those hydrogens are going to go. We'll see. We'll add those in a bit. Let's start with just the numbers of electrons for everything. So sulfur is in the same family as oxygen, so it also has 6 electrons. And no charges that we have to take care of here. So connecting our dots here, everything gets 1 bond. And then sulfur still has 2 electrons available, which is a little bit weird, right? But remember, sulfur is going to be able to make more bonds and have more than an octet, and this is going to be an example of that. So even though it has 4 bonds and an octet now, it still has these electrons from its own valence that need bonds. So I'm going to make bonds from these electrons out here to that sulfur. I'm just going to erase them and redraw the bond down here so that it looks a little bit cleaner. Okay, so the sulfur is good. It has more than its octet. And these oxygens, 2 of them are okay. So the 2 kind of on top and bottom here have their octets and they look good. The other 2 seem to be missing something though. They have just that 1 lone electron. And so that is something that could pair up nicely with our hydrogens, like so. So that is the structure for sulfuric acid. And don't worry about knowing any of these names. You don't need to right now. What you need to be able to do is to translate between formulas and Lewis structures to start. So hopefully those went well. And if you are still sort of a little bit unsure, it may feel like a million years since you took Gen Chem. If you need a refresher, there's a Drawing Lewis Structures rules document on our Canvas page. Go ahead and look at that. And that has a nice step-by-step breakdown. I know I'm going a million miles a minute here, but we want to get through all this Gen Chem stuff and get onto the fun OChem stuff that's coming next. So we really want to get familiar with these Lewis structures and feel comfortable with them very quickly, because almost immediately I'm going to transition out of drawing Lewis structures and draw things in line angle formula instead. So what is line angle drawing? So that's a type of structure representation that simplifies carbons and completely ignores hydrogens. And that's the purpose of this, is just to simplify and save time. When you get to bigger organic molecules, like I said, it's going to take a lot of time to draw out every individual hydrogen. Imagine you maybe have 30 in a molecule that you'd have to draw. So that's why we like to simplify, make them just a different readable structure that's much, much quicker to draw. So to start off, here are a couple of the rules for drawing line angle. Every time you want to draw a carbon, you're either going to draw an end of a line or a vertex. So each vertex that we draw and any endpoints are going to be carbons. So this may seem a little bit weird. Hang on for a moment. So any endpoints of a line or vertexes in a line are going to be carbons. And then we just totally ignore the hydrogens unless they're drawn on a heteroatom. What's a heteroatom? It's anything that's not carbon. So let's look at a couple of examples to help clear this up a little bit. Here's a molecule called butane. You don't need to know about the name yet, but it has 4 carbons in it and a bunch of hydrogens, 3, 5, 7, 10 hydrogens. So that took me, 10, 20 seconds to draw, but I'm going to be able to draw butane in a line angle formula in probably less than 3 seconds. Here we go. There we go. That one was a little sloppy, so I am going to redraw it, but that's the idea, is that these two are the same thing. So you see how much faster that one was? Try drawing them both out for yourself if you don't believe me. So when I say vertex and endpoints, now we'll be able to see it a little bit more clearly. So when I say vertex, I mean these points here, where there's kind of a kink in this line, those represent carbons. And then the endpoints, here and here, also represent carbons. So if you are having trouble seeing this a little bit, totally okay. What you can do is just sort of draw in C's on each of those vertexes and endpoints to remind yourself, oh yeah, that's a carbon, no problem. And then what we would do to remind ourselves of how many hydrogens there are is just fill in as many hydrogens as it takes so that all carbons have an octet. So here at the end, this carbon here, if we gave it 1, 2, 3, and then it's already got a fourth bond, it would have 3 hydrogens around it. We just didn't bother to draw them in. So that's how we save a little bit of time, space, and effort in converting our Lewis structures to something that's just easier to deal with. So here's another example here of ethanol. So this is the example with a heteroatom. We have 2 carbons here. Let me show you how easy it is to draw 2 carbons, 1, 2. There we are, again, reminding ourselves that this, oops, I want to do that with a highlighter. This end is a carbon, this end is another carbon. And then to fill in the O and the H, we draw another line here for that O. And because this oxygen here is a heteroatom, we must draw in this H. That's required. Otherwise, we're going to assume a formal charge there. We'll get more practice on this later on, so this is just an introduction to get you started. So the other point that I would like to mention is we're talking about vertexes and endpoints. So if we go back to our vertex here in this kind of pink color, that's 1 carbon. And then in that slightly different purple color, the endpoint there is a carbon. I just want to make it really, really clear that this right here, that's not a carbon. That is just a line that shows this vertex is bonded to that oxygen. So there's no carbon there. Try not to get that too confused. And again, practice drawing these out and annotating with adding C's and H's as needed until you feel more comfortable with it. Like I said, this is going to be a really key drawing tool in the rest of the semester, so we want to practice it a lot now to really get it down pat. So in order to practice, let's do a few more examples. So pause the video here, try this first one, which is called cyclohexane, and then check your answer with me after you're done. So to draw cyclohexane, if you're not sure, always practice your counting. I promise you, counting seems like a silly thing to need in organic chemistry at an undergraduate level, but you really need it. I need it, and I'm a professor. So counting up your carbons is always a good thing. So we have 1 here, 2, 3, 4, 5, 6. And you notice that they're sort of going around in a ring or a cyclic type of format. So there's a good reason for that, and that's the reason why we call it cyclohexane. More on that later, but you can see that we just need to arrange 6 carbons in a ring format. So the best way to do that is just by drawing a hexagon. Oops, that one side got a little bit wonky. Let's make that a little nicer. There we go. So that is cyclohexane. Just as easy as that. I hope you like hexagons because we'll be drawing a lot of them this semester. If you're not good at that, just practice. I promise it gets easier. So hopefully that one went well. Let's try this next one. Acetic acid, pause here, make your guess. For acetic acid, there's definitely less atoms here, so hopefully it'll be a little bit easier, but we have this CH3 at the end here. So there's 2 carbons, 1, 2, 1, 2. And then to draw in these O and OHs, since those are heteroatoms, we have to draw all of that in. Like so, there's our doubly bonded oxygen at the top. And then our single bonded oxygen. And again, this hydrogen bonded to the oxygen is mandatory, so make sure it gets in there. How'd you do on this one? Hopefully it went all right. Let's get to this next one. This looks like a lot here, this last one called triethylamine, but I promise it won't be too bad. Take a guess, see what you think, and then check with my answer in a second. So to draw this one, there's a lot of different ways you can go about it, but I like to start with the most interesting thing, and that's this nitrogen here in the middle. So I like to draw kind of from the inside out, but you draw this in any way that makes sense to you. And I'm running out of room here a little bit, but we'll do this kind of small at the bottom. So I'm going to start with that nitrogen. Again, we have to draw that in. We can't simplify it. And then on each sort of side of that nitrogen, it seems like we have 3 of these CH2, CH3 groups, right? CH2, CH3, CH2, CH3. So those are very symmetric, which means that we can pretty much just simplify those to CH2, CH3 groups that look something like this. So here's CH2, CH3, a little wobbly on that one, that's okay. CH2, CH3, CH2, CH3. And that's it. So remembering that each of our endpoints here is one of these CH3 carbons, and each of our vertexes is a CH2 carbon. Okay, hopefully this color coding is helping you out a little bit. Again, we're just flying through this to get you started, and you'll need to practice a lot on it. So hopefully those went well. And if they didn't go super well, that's totally okay. There's going to be a lot of difficult things we have to tackle this semester. So this is maybe going to be one of the first. And that's the way that you do it, is just by practicing. Practice, practice, practice a lot. Practice drawing a bunch of bad hexagons, and they'll slowly start to get better, I promise. So practice your Lewis structures. Practice your line angle drawing until they feel really familiar, confident. And also, we didn't do a ton of identifying formal charge in the video today. Hopefully you did a bit of that in Gen Chem, so I'll make sure that you get some homework problems and practice problems that allow you to do that as well. And if this feels comfortable to you and you're ready for the next thing, you can feel free to go ahead and look forward to atomic orbitals and valence electron configurations. That's what we'll be talking about in our next video. If you have any questions, make sure to post them in the discussion forum so that you and your classmates can respond to one another and help each other out. And if you're really stuck, make sure that you email me and come to my office hours and we'll chat about it. All right, take care, and I'll talk to you all in the next video.